Boa tarde, buenas tardes a todos, a audiência, a todos e todas que estão aqui em mais essa tarde de nossos seminários. Hoje temos o seminário número 40, né? A sessão número 40 do seminário. É um grande feito, né? Chegarmos até aqui. E para essa tarde de hoje temos dois palestrantes aí, por coincidência, a primeira palestrante é a professora Maira Aguiar, lá do BECAM na Espanha, em Bilbao, é brasileira, e aí está trabalhando já em vários lugares, portuguesa, e por aí vai, vocês vão saber um pouco da vida dela daqui a pouco, e apresentada pela professora Rosana Lopes Cruz, e na sequência nós vamos ter a apresentação do professor Manolo Gonçalves Burgos, também da Espanha, da Universidade de Sevilha, que vai ser apresentado pelo nosso colega Diego Souza, aqui da organização. Por favor, Rosana.
Okay, muchas gracias, Sandra. It's a pleasure for me to introduce Maira Aguiar, doctor, and some other things that you can see. Bien, voy a hablar, lo tienen en pantalla en inglés, en portugués, y voy a hablar en castellano, dado que el público es bastante multilingüe. Ella es epidemióloga matemática que trabaja en dinámica de las enfermedades infecciosas con un perfil de investigación multidisciplinar. Está formada en teoría de sistemas dinámicos, procesos estocásticos, dinámica no lineal, análisis de bifurcación y bioestadística, poseyendo doble doctorado europeo, un doctorado en ciencias de la vida por la Vrije University de Ámsterdam, Holanda, y doctorado en biología de las poblaciones por la Universidad de Lisboa, Portugal. Es una ex becaria Marie Curie de la Universidad de Trento, Italia, y fundadora y líder del grupo de Biología Matemática y Teórica del Centro Vasco de Matemática Aplicada, BECAM, en el País Vasco, España. Sus intereses científicos abordan cuestiones muy interesantes e importantes de la biología y medicina, en especial enfoque con la moderación en la epidemiología y la salud pública. Ella es miembro del grupo de trabajo en salud pública y como tal actualmente se encuentra ayudando a los gestores de la salud pública vasca y al gobierno vasco durante las respuestas del COVID-19. Para mí, nuevamente repito, un placer presentar a Maira, una gran investigadora que el día de hoy nos dará la charla on the origin of complex dynamics in multi-strain dengue models, en el origen de la dinámica compleja en modelos de dengue multicepa. Maira?
So, again, thanks for the invitation. My talk today would concentrate on complex dynamics, and more focused on epidemiological systems, specifically on multi-strain epidemiological systems. And my case study would be dengue fever, that most of you, at least living in tropical countries, have heard about it. My name is Maira Aguiar, and I'm the group leader of Mathematical and Theoretical Biology in the Basque Center of Applied Mathematics in Bilbao, Spain. I'm not going only to talk about the complex dynamics that one can find in these multi-strain models, but also what is the impact of finding such a complex dynamics on public health interventions. We all know that chaotic scenarios on epidemiological situations are under reviewed, so it's unexplored, and any kind of insight one can give from these systems would be very helpful for public health authorities. Briefly, introduction about dengue fever epidemiology and why or how or which are the assumptions one needs to consider when we want to develop a model to describe the dynamics of this disease, which is a viral mosquito-borne disease. It's a leading cause of illness and deaths in the tropics and subtropics, although it's not only restricted to those areas anymore. Back 2012, we had a huge outbreak of dengue fever in Madeira Island, which is part of Portugal, although it's an island. It's part of Portugal, and we have local transmission already going on in several areas of the south of Europe. More than 1/3 of the world population are living at areas at risk of acquiring the infection, and this part here is concentrated only in the tropical area, have shown what is the risk of getting infected in different countries on the tropical surface of the Earth. Here we see that the predicted global risk in red, we have high risk, and in blue, we have low risk. And this is an update from the previous paper published in in Nature in 2013. Dengue is a very special, very interesting disease because although it's already a vector-borne disease, there are 3 viruses that can cause the infections. Those 3 viruses are different, so you can get, in theory, 4 different infections, which with each one of those viruses. And because those viruses are antigenically so similar, the secondary infection with an heterologous virus would generate or would increase the risk of the individual acquiring a more or developing a more severe form of the disease called dengue fever, dengue hemorrhagic fever. I like to show this map here for you to see how fast and how good those 4 serotypes were in spreading and establishing in different areas of the world. So what we know that in 1970s up to today, the 4 serotypes have been coexisting in the Southeast Asia, which make this area of the world a very interesting area to study the coexisting of those serotypes. So 3 topics or 3 points here that we need to consider when we want to develop a model to describe dengue dynamics. We know that infection by one serotype will confer lifelong immunity to that serotype, meaning that once you are infected, let's say with dengue 1, you no longer would be able to get infected with dengue 1, or at least symptomatically infected, okay? So after a primary infection, you have a period that we call short-term cross-immunity period. In the literature, it says that this short-term cross-immunity period lasts between 3 to 9 months. But when talking to specialists, we know that this cross-immunity period can last up to 2 years. The disease has a wide spectrum of clinical presentation. Most of the cases in its primary infection are asymptomatic or very mild that do not harm the individual, meaning that the mobility is not affected. But after recovering and eventually becoming infected again with heterotopic virus, which means that a different virus causing a primary infection, the individual can develop a severe form of the disease, which is classified by leak or hemorrhagic symptoms. And it is associated with epidemiological studies associated with a process called antibody-dependent enhancement that I will try to describe very quickly using this scheme here. So what I have here is immunological response sketch for a primary dengue infection and for a secondary dengue infection. And the first one applies to any infectious disease caused by a viral pathogen. It's basically this virus will invade the healthy cells and will reproduce and will generate more viruses. The immunological response start acting first using an antibody which is unspecific but very good into binding to this virus and neutralize the disease. It's called IgM antibodies. And while these antibodies are clearing the infection, you also have a development of a specific antibody called IgG or memory antibody. And this antibody here is the one responsible for the lifelong immunity against this serotype. Let's say that serotype is called dengue 1. After you go through this process, you are full of this IgG, which is specific for this virus, and you no longer will be able to acquire infection with this virus. Okay, after the infection is cleared, you have a level or a huge concentration of those antibodies plus some other T cells, etc., which will confer the so-called temporary cross-immunity period. When this level of antibodies starts to drop, the individual is considered susceptible again, so able to acquire a new infection. So if you think that after a period of, temporary cross-immunity, you are able to get another infection, if you enter in contact with the same virus, what happens is that your immunological response will recognize that virus. You increase the level of this specific IgG antibody. This specific IgG would be able to bind to this virus and would immediately clear the infection. So even if you get infected with the same virus, the immunological response would be so fast because of this pre-existing antibody that you no longer will either feel symptoms nor even transmit the disease. Okay? But what happens if this virus is different from the virus causing the primary infection? So we call it homotopic when it's the same and heterotopic when it's different. What happens if the secondary infection is caused by a heterotopic virus? What happens is the following. Remember that I mentioned that this virus is very closely related to the other 3 serotypes, and the immunological system recognizes it at first glance as being the same. So instead of starting a completely new immunological response with IgM and IgG, the organisms try to neutralize this new virus using the pre-existing antibody, which is specific to the first infection virus, but still able to bind it to the new virus. What happens is that you have now a complex of IgG virus, which is able to bind it to this virus, but is unable to neutralize the virus. So this complex goes inside the cell to be destroyed. However, the virus is still active. So instead of being destroyed, this virus is kind of being helped by the immunological system to replicate faster than in a primary infection. So you have a huge amount of viruses here. And as soon as the immunological system recognizes that the IgG, the pre-existing IgG is not good enough to clear this infection, the immunological response restarts again with IgM, but now in a much higher scale, which would lead to hemorrhagic symptoms. Okay, so basically the ADE processes refer to primary infection giving temporary cross-immunity period and secondary infection with heterotopic viruses causing hemorrhagic symptoms and leading to a severe form of the infection. Okay, so as I was saying, the majority of the secondary infection occur at space of more than 6 months, and that is really well known, especially in the tropics. Not only because of the seasonality, the disease is a seasonal disease transmitted by vectors, but also because of this temporary cross-immunity that I just described to you. There is no specific treatment for dengue, and all the severe cases with hemorrhagic symptoms will require hospitalization, which means that most of the data that we have from the databases of notified disease are those who felt some symptoms, are those who somehow were admitted to hospital, and probably those which were suffering at least a secondary dengue infection. Okay, there is no vaccine which is efficacious for against the disease. So there is a single licensed vaccine that was produced by Sanofi Pasteur. This vaccine started 20 years ago to be studied, and after a huge phase 3 trial, which covered most of the different areas of the world, Asian Pacific and Latin American countries, the result was basically the following. We had different efficacies for different age groups. So children between 2 to 8 years of age experienced a positive vaccine efficacy for the first 2 years, and this vaccine efficacy dropped to a negative level at year 3 and was kept into the negative level, which means that after 3 years of receiving this vaccine, those so-called children which received the vaccine were developing disease much more than those which didn't receive the vaccine. That's what we call negative vaccine efficacy. In the second hand, we have here individuals over 9 years of age, and those individuals had a positive vaccine efficacy along these 4 years. However, we also saw a drop of the vaccine efficacy at year 3 with a huge confidence interval reaching the negative values of vaccine efficacy and dropping even further. That's the latest data we have, and led the manufacturer at first instance to not vaccinate individuals below 9 years of age because of this result observed here. We are going to discuss a bit about that a bit further on. Okay. And then recently, 1 year ago, there was the results from another vaccine company, Takeda, from Japan, which is also working in a similar type of vaccine comparable to the Sanofi vaccine. These results of the trials were published, and we had evaluated the efficacy in different times period. So after 12 months and after 16 months, I guess this vaccine trial is completing now 2 years or 2.5 years. Those results are publicly available. And what we observed here for the Takeda vaccine is the following. After 12 months, we had a relative good overall vaccine efficacy of around 80%. And this vaccine efficacy started to decrease over time. And the signal here is that vaccine efficacy, as we all should know, is not a static measure and will depend on the type of vaccine and on the individual which is receiving this vaccine. Okay. For the experience we had for the Sanofi vaccine, that we had problems with individuals very young, which were in its majority seronegative. And by seronegative, I mean those individuals which have never been infected with any dengue virus before. There was a significant difference between seronegative and seropositive individuals, which was also observed in the Takeda vaccine. So we can see here the overall vaccine efficacy for seropositive is much higher than the vaccine efficacy for those which were seronegative individuals. So in the bottom here, I had the figures for the Sanofi that I would like to compare with the vaccine efficacy for the Takeda. And what we observe here is the following. In the Sanofi vaccine, although we expected to have a tetravalent vaccine, we end up having a kind of bivalent vaccine with dengue 4 and dengue 3 with a good efficacy overall versus an intermediate vaccine between dengue 1, dengue 2, dengue 1 and dengue 2. And for the Takeda vaccine, we have more or less the same result, which have a dengue 2 with almost 100% vaccine efficacy, and that is explained by the fact that the backbone of this vaccine was made by dengue 2. Of course, you would be completely immune against this serotype, but then you have different vaccine efficacies for different serotypes, and that it's kind of an alert for us when we want to analyze vaccination. But of course, before looking at vaccination, we should have a framework, a model, and to have a model, we should define the question we want to answer. And to define the question we want to answer, we have to see which data do we have. So here we have an example among several types of data we have for dengue. We have serotype data. This is for Puerto Rico. We have data for eggs of mosquitoes. This is for one region in one of the state of Brazil. You have incidences. This is for Chiang Mai, one province of Thailand. And the incidence data can be divided or splitted or geographically distributed by provinces. This is the map of Thailand, where we have 76 provinces, and the monthly incidence for each one of the provinces can be described. And also we have data on within host level, meaning the viral load and antibodies load and so on and so forth. The work I'm going to present today relies or is validated by incidence data, and my framework is able to describe the oscillations we can see in this data here in red, giving the blue trajectory of my model. So how much complexity do I need to have this kind of matching? I'm going to show to you now. Okay, before that, just make a small propaganda. We have just published a review paper on the 10 years mathematical models developed for dengue fever epidemiology. If you are interested on that, the paper is really nicely, modestly speaking, so it is already available and is open access. Okay, so I mentioned to you all that mumbo jumbo of the assumptions and what happened epidemiologically speaking on dengue, and what I can summarize, it's written in this slide. I need 5 main ingredients to develop a model to describe dengue dynamics, and these ingredients are listed as model parameters, where among those 5, 3 I know very well. First is the infection rate beta, everybody know, the recovery rate gamma, and the demographic rate. And I ended up with 2 parameters here that I need to estimate, because there is no such information. We have kind of a range, an idea where these parameters would be, but there is no animal model, and of course we need data to estimate those. First of them, it's cross-immunity period. We know that in the literature we find that varies between 3 to 9 months, but it can last up to 2 years. So we have a range, but we don't know exactly what is the impact of this cross-immunity within the force of infection overall. And the second one, very important, is the rate Also the secondary infection contribution to the force of infection, or ADE ratio, which would tell me how much more individuals in a secondary infection would transmit the disease as compared to individuals in the primary infection. And with these 5 main ingredients, I can write an N-strain epidemiological model that basically divides my population into 6 large groups, where I have the naive individuals or susceptibles or seronegative individuals, which are able to acquire a primary infection with a serotype I, and in my case, I can be dengue 1, 2, 3, or 4. These individuals recover from this infection with serotype I, and after a period of temporary cross-immunity alpha, become susceptible again, but now with a pre-existing antibody against serotype I. So this guy here can then get a secondary infection now with serotype J, having seen serotype I. And finally, if this guy recovers, we have the end of the model, the model framework. I assume only 2 possible infections, basically because there is very low frequency of tertiary and quaternary infection. In fact, this data is not even available in hospital databases. This data is observed when you have a cohort and you follow up a group of people and count how many infections they have. What is said is that after a secondary infection, your immunological system is so much boosted that you no longer is susceptible to get a tertiary and quaternary infection. And if you get, though, you are immediately able to fight against this infection and not able to transmit the disease. And that's the assumption we have for now. Okay, so, but as a good biologist, I would like to investigate, even though without significance to the real life, to investigate this system started from the minimalistic up to the most complex one. And in order to investigate this N-strain epidemiological model, we can analyze the system as follows. We can start from a very basic system where we assume only 1 strain and 2 infections. That, remember, that's not biologically because of the temporary cross immunity and the lifelong immunity we have, but we can see what this model brings to us in terms of dynamical behavior. So the diagram is the following. You have a seronegative individuals acquiring a primary infection, and after recovering, it becomes recovered from the primary infection. And after a temporary cross-immunity period alpha, you are susceptible again, able to get a secondary infection, okay? So we have a system of 6 ODEs, so a 5-dimensional system. And interesting to notice that we have no vector dynamics explicitly. So for the seasonality part, we simply plug in a cosine function into the transmission rate parameter. And I highlight here the 2 parameters we have no information in terms of animal model or data. So we have the phi, which will estimate how much more these individuals in a secondary infection transmit the disease in comparison to these individuals in a primary infection with infection rate beta, baseline infection rate beta. And we have the temporary cross immunity after recovering from a primary infection, how long it takes for you to become susceptible again and acquire the infection. Again, only 2 possible infections are possible. And I compare the system with and without seasonality. And what I can tell you after a lot of research is that I can only get any kind of dynamical behavior, meaning outside fixed point area, is when I assume my alpha to be equal 52, meaning that individuals can get infected, recovered, and immediately infected again. So we have no temporary cross immunity, another sign that is not realistic for dengue. And I have to assume my phi to be 2.6, or I have to assume that individuals in the secondary infection transmit the disease at least 3 times more than individuals in the primary infection. For the non-seasonal model, I show here a bifurcation diagram for temporary cross immunity, for example. And you see that we have a fixed point occurring when we have almost no temporary cross immunity. So we have very few time after getting recovered from the infection and becoming infected again. And this this bifurcation point here become complex as soon as I add seasonal forcing. The same was observed for the ADE ratio. So for the contribution, I have a hope bifurcation here when my phi is between 1.5 and 2 and become chaotic. And I will prove to you that it's chaotic after including the seasonality into the system. And we had done this experiment for different parameters, for seasonality itself, for import itself. And what we could observe at the end of the full analysis of this model is that complex dynamics, which is needed to explain the oscillations we see in the data, is restricted to a small parameter region where no temporary cross-immunity should be assumed, and individual and secondary infections should transmit the disease much longer than individuals, with much more strength than individuals in the primary infection. And this chaotic window here is just confirmed by the Lyapunov exponent, which is positive by assuming antibody-dependent enhancement to be contributing much more to the secondary infection than a primary infection. So my phi parameter should be larger than 1. Okay. Okay. Qualitative, when I look at the model output in blue and the data, I would not need any statistical test to reject this model, but it was a good experience to investigate this model, and we are further working on this model, in fact, to see any kind of effect such as spillover event for new pandemics. The model is very rich dynamically, but its richness occurs in a region which is not realistic for dengue, maybe for another disease. The model shows irregular outbreaks every 25 years and is not data-like. Plus, you have to restrict the parameter set to be no temporary cross-immunity, and individuals in a secondary infection transmit much more than individuals in a primary infection. Okay? Good. I can increase this model and I can add the vector dynamics. So instead of getting the six ODE system, I get the 8 ODE system because I just couple SI model for the vector, and what I get is the following. The chaotic dynamics or the complex dynamics is moved from up to down, which is a bit closer to the reality in the sense that you no longer need to restrict secondary infection to transmit more the disease than primary infection, but still you have this output here, which looks like more, a limit cycle with a very irregular outbreaks, but every 6 years or so, which is not data-like either. So the third step is to include the strain structure in the model. Remember, this is the same model I have shown to you. Susceptible individuals become infected for the first time, but now this individual can be infected either with strain 1 or strain 2. After recovering, this individual go through a period of temporary cross-immunity alpha and become recovered with a pre-existing antibody against this virus causing the primary infection. And then this guy here can get a secondary infection with strain 2, having seen strain 1 first, or secondary infection with strain 1, having seen strain 2 first. So this is the same model now with strain structure. I highlight again the parameters that we are interested on. So the phi and the alpha. Again, no vector dynamics is explicit. So my beta is simply, my transmission rate has a cosine function in order to mimic the abundance and the decrease of vector, which means that increase of transmission and decrease of transmission. And because we do not have the vector transmission, the force of infection will depend from whom you are getting the infection, okay? So if this guy here, in order to become primary infected, he can acquire the infection from individuals in a primary infection or from individuals in a secondary infection. So that's why the force of infection here is basically a sum up of primary infections plus the phi on front of secondary infections. Again, only 2 possible infections allowed. And the first interesting thing that we found out in this model was that we have a significant difference in dynamics once we assume temporary cross-immunity or not. So in the case of no temporary cross-immunity, so alpha equals 52 means 1 week after recovering, becoming infected again, you have this chaotic behavior for a parameter region of individuals in the secondary infection transmitting the disease 2.5, 3 times more than individuals in the primary infection, similar that I have shown for the simple version of the model. However, as soon as you include this temporary cross-immunity of at least 6 months, a new chaotic window appears in a completely different parameter region of phi smaller than 1, and that is, besides being more realistic for dengue, because when you assume that individual in a secondary infection would be rather hospitalized and not transmitted the disease as much as those suffering an asymptomatic infection, Also, the troughs are much more realistic in terms of stochasticity, and overall, it opens a new way to evaluate the system, no longer needing to restrict the increase of transmissibility in the secondary infection state. Okay, so that was our finding, basically my PhD. We found the new chaotic window for a region of phi smaller than 1, and we focused our further research in this parameter region value. I hope you are all listening to me. I hope I didn't. Can you
Todo
hear
correcto.
me?
Todo
Okay.
correcto.
Muchas gracias.
Tá bem.
Okay, good. So, and then we concentrated our effort in looking this new parameter region, which is super rich, as I'm going to explain to you now. First, the non-seasonal model gives already so much dynamic structure from Hope, pitchfork, torus, and tangent bifurcation, including deterministic case, which was something really interesting to look at. So via bifurcation analysis, we could find all those bifurcation points, some isolates happening here as well. And via the Lyapunov exponent, we confirmed that the parameter region of phi 0.5 means that individual in a parameter infection would transmit 50% more than individuals in the secondary infection. It's chaotic, and we were very curious to see which kind of behavior we would have in terms of time series. So remember, that's for the non-seasonal model. So we have irregular pattern every 5 years. And as soon as we add seasonality, we get realistic pattern with irregular, yearly, and smooth outbreaks. That qualitative describe very well the model and the data, as we can see here. So in red, I have the data for Chiang Mai, and in blue, I have the model simulation for this 2-strain model. And again, it is a chaotic system, which means that I cannot match this 30 years of data, but the patterns are there, and we can have a very interesting analysis or a very interesting result when we look further into this system. And that's what we have done as well. So for the seasonal model, where we can match the data, I'm sorry. The parameter region here, my phi, the ADE ratio, the ADE rate is 0.9, which means that I assume the difference between primary infection and secondary infection to be only 10%, with secondary infection transmitting 10% less than those in the primary infection due to hospitalization. That would be in this area here. We have a dominant Lyapunov exponent of 0.118, which gives, in terms of prediction horizon, around 8.5 years, which is excellent. We know that as soon as you add, stochasticity, this prediction horizon will decrease. But I mean, to be able to predict at least 1 year ahead, a dengue epidemic would be of a major importance for a public health system in endemic countries. So this is only an exercise we have done for this parameter region. In black, it's my model simulation. I perturb a little bit my model, and then I run again, and I plot together both trajectories, and we can see that for the first 9 years, both trajectories are very well agreeing. And after these 9 years, I no longer can trust my system because of its chaotic. And we know that a chaotic system has a short period of predictability and a long period of unpredictability. So we would need to start the analysis again from that moment on. So we had time to look at the similarities between the system, assuming 2 strains, 3 strains, and 4 strains. And independent of the number of strains we add into the system, we get always the same structure, either for temporal cross immunity, or here it's the state space for the infected with the same 5-parameter value. So this chaotic behavior is always observed in the same parameter region, in the same parameter set, in the same application points. And to give you an overview of that, I will compare the 2-strain minimalistic model with the most complicated one, which assumes 4 different strains. The system is exactly the same. You have seronegative individuals becoming infected for the first time with strain 1 and 2. Please note that there is no asymmetry between the strains. So 1 and 2, 3 and 2 is only a label. After primary infection, you recover, and after temporal cross immunity, you become susceptible again, having seen a given strain. and you can only get a secondary infection with a different strain from a primary infection. This is for 2 strain, this is for 4 strain, and you see that for 4 strain we have a larger possibilities of combinations of strains, and you end up with 10 ODEs versus a 25 versus a 25 ODE system, so 9 versus 24 dimensional system. This one is almost impossible to do anything analytically, but in terms of simulation, qualitative, both models give the same result, so they are able to describe the pattern observed in the data. Quantitatively, we can see that the bifurcation points occur at the same point. So in red, I have my 2-strain model, and in green, I have my 4-strain model. Also, in terms of Lyapunov exponent, which are matching in the same parameter region, we have no difference in the structure of the dominant Lyapunov exponent and the same prediction horizon. So I do not gain anything but complexity by adding strains. And that was another very interesting result, that the number of strains you add in your model is not important. It's not an important thing in order to give you this complex dynamics that you need to describe the data. And of course, by parsimony, we just select this simple model to be extended to be evaluated for the vaccines. Okay, so the vaccine was ready. We had a very good model, so we decided to extend the model in order to evaluate the impact of this vaccine that was just licensed. Again, the model is the same. However, because of the restrictions of, please, Roxana, if I need to stop you, let me know, okay?
5 minutes, Maira.
Thank you. I would be very quick here. So for the introduction of the vaccine, what we have done is we took our 2-strain minimalistic model and we stratified by 2 age groups. So we have individuals under 9 years old, which were not able to get the vaccine. Remember that I showed the vaccine efficacy going to the negative area. We have those individuals between 9 to 45, above 45 years old, which were not part of the trial, so they could not be vaccinated. And you have the age group between 9 to 45, which are those which could eventually receive this vaccine, okay? So we have 3 age groups, 3 different age groups. Individuals below 9 and above 45 are not vaccinated, but living in endemic areas can go through the disease stages because they can get infected anytime. So you have a contribution for those age groups where susceptible acquire primary infection, recover secondary infection, and eventually going hospitalized because of the severity of secondary infection for this group and this group here. And this group, which is target for the vaccine, can be vaccinated in 2 different ways. Either you are vaccinated as seronegative, or you are vaccinated having seen already in your life at least 1 dengue virus. So you are seropositive. And what we saw in the vaccine trial is that those individuals receiving the vaccine after having been infected with a dengue virus at least once before receiving this vaccine would have the vaccine acting as a boosting and would protect against further infections and would remove these individuals from the susceptible with a pre-existing infection to the recovered class, decreasing the probability of developing secondary infection, decreasing the hospitalizations we can find when you are in a secondary infection. However, when you are vaccinated as seronegative, this vaccine would act as a primary natural infection. You remove these individuals to a sensitized class, and this guy here, by acquiring a primary natural infection, would then develop severe symptoms as a secondary infection, and here we have an increase of hospitalization. Now, what is the impact overall in this population? What we do, we just match the data for 5 years, the last 5 years of data we have, and we check what happened in the following 5 years, given the limitation of the prediction horizon our system has. This is just a summary, just to remind you that we have problems here in children which were seronegative in its majority with a negative vaccine efficacy, and we have a positive decreasing vaccine efficacy for those older than 9 years of age, which were in its majority seropositive. Those informations were found in the report of the WHO, very hidden. Vaccines were not recommended for children under 9, but we have seronegative in children of 10, 11, 12, and 30. So what the assumption of our modeling would be, individuals which were seronegative would have a lower vaccine efficacy than individuals which were seropositive when receiving this vaccine. And we evaluate two scenarios. The first scenario is that we implement the vaccine without any kind of immunological screening. So you just get the population, you vaccinate a percentage of that population without differentiating, you are seropositive, you are seronegative, just vaccinate everybody. We match the data for the first 5 years, we introduce the vaccine here, when we let it run for 5 years, and what we observed was, without immunological screening, you have an increase by 25% on the hospitalizations of that population. When we do an immunological screening, what we do is select seropositive from seronegative, and you vaccinate only seronegative. And here it's in a very small, let me see if I can increase it. No, I can't. I have a very light blue line here showing that when you do this screening, you have up to 40% decrease in hospitalization. And the key message of this study was to say, hey, this vaccine is a risk for those which are seronegative. If you want to use it, please screen your population and admit only those which are seropositive and not which are seronegative. That was an endless discussion, and only a few years later came a result on the serological point of view, which confirmed our assumption, showing that individuals seropositive and seronegative here are completely different, with this distribution not overlapping at all. However, when you look at individuals independent of age, but at immunological stage, they are pretty much similar. And those individuals which were seronegative had most of it a risk of developing severe disease after being vaccinated. So the message was, please do not vaccinate individuals which are seronegative, because the serostatus prior to vaccine is the most important issue for this vaccination. And that was something, a fight that we had for 2 years. So I'm about to finish. I'm just going to give an overview of the dengue vaccine dilemma that started in 2016 and was almost finished in 2019. So in April 2016, this vaccine was recommended by the WHO, even though the results have shown that there was a huge difference between seronegative and seropositive individuals. In 2016 and 17, even before the final license of this vaccine, the huge vaccination programs were implemented in the Philippines, where at least 10% of the age group vaccinated were seronegative. And also in the south of Brazil, which dengue is not really a big deal, and most of people would be seronegative. Everybody on the modeling side was, we were very worried because there was no pre-vaccination testing. And of course, our noise made Sanofi Pasteur start to make some tests on the previous samples they had. And the result was like, in fact, those seronegative should not be vaccinated, and these vaccination programs were suspended. But that was something that it lasted about 2 years, and more than 1 million people, if you think that 10% of million people were seronegative, in the new future, in the soon future, we are having to have a problem with those people. So only middle 2018, WHO released new recommendation for this vaccine requiring pre-testing, which was a bomb that could have been avoided since 2 years ago. So this is one of the examples, some of the papers we have published about this issue on the Sanofi vaccine. Now, we are looking at the Takeda vaccine, and we see that the results are really similar. Remember that I show you the graphic showing the vaccine efficacies for 12 months and 18 months. And what we see that as time passes, the vaccine efficacy is decreasing, and there is a huge risk of negative vaccine efficacy as well happening in the Takeda vaccine. So efficacy and safety conclusions for this vaccine will require long-term surveillance, and that's what we are hoping for. I stop here. I thank you for your attention. I would like to make an advertisement about the mathematical models and epidemiology course that is going to take place in Beckham, start on 25th of March. There is no possibility to register anymore, but I guess most of your students or colleagues have been registered, so I hope to see you soon on Friday. And please stay tuned and follow us on Facebook and Twitter to get to know our activities. Thank you for your attention.
Thank you very much, Maira, for your presentation is very good. Do we have questions? Let me see. Está abierto el audio, así que pueden levantar su manito o hablar. Bien, mientras van pensando, Maira, ¿y han tenido en cuenta la dinámica del mosquito?
Sí. ¿Respondo en castellano o...?
Sí, o en portugués. ¿En portugués?
No, practico mi castellano. Después hablo,
correcto.
Para que los estudiantes de Beckham puedan entender un poco. Sí, tenemos investigado la dinámica de los vectores. ¿Qué pasa? Es que nosotros no ganamos nada en adicionar el vector, sino tenemos una pregunta directamente a los vectores. Entonces, que verificamos es que la adición de la sazonalidad en la tasa de transmisión es suficientemente bueno para describir la dinámica sazonal de la doença.
Correcto.
Si me permite, just for the students, Roxana has asked about the explicit vectorial dynamics into the model. And what I mentioned to her is that if you do not have a specific question for the vector, the extra equations for the vectors are not justifying the extra complexity. So the cosine function does the work.
¿Alguien que quiera hacer alguna pregunta? Una pregunta más, Mayra. ¿Y el dengue hemorrágico está considerado aquí?
Sí, esto sería la segunda infección.
Correcto.
¿Qué pasa? Es que la primera infección es 90% asintomática o mucho levecita. La segunda infección puede generar diferentes tipos de síntomas, pero siempre asociado con una sintomatología casi 100% de los casos. Y estos impactos son los casos que tenemos como dados. Entonces, asumimos que los dados que tenemos son de personas que están en una segunda infección más leve, más severa, pero ha visto ya una variante del virus, un serotipo, posiblemente están desenvolviendo una respuesta inmune a una segunda infección.
¿Alguien que quiera hacer alguna pregunta?
Eu gostaria de fazer,
Sim, Sandra, claro.
Maira, uma pergunta. Muito obrigada pela apresentação, excelente. Mas eu tenho trabalhado um pouco com um grupo em algumas coisas assim, com a Covid também, né? Não é minha especialidade, estou aprendendo com eles. Aí eu vi que você usava no seu modelo aí da dengue, antes do modelo de vacina, né? O outro modelo que você apresentou, o parâmetro beta dependendo do tempo, né? Apresentou ele com... Você não usou nenhum outro parâmetro dependente do tempo?
Não.
Do modelo, né? Isso foi porque eu estou perguntando isso, porque a gente teve essa pergunta de um revisor, né? Que nós usamos também no nosso modelo, inclusive no modelo de vacina, esse parâmetro dependendo do tempo, e não os outros, porque a dinâmica, né, ia ficar muito complexo, né? E nós fizemos uma análise de sensibilidade e demonstrou que realmente o parâmetro beta era o parâmetro que mais influenciava aí da questão. Vocês fizeram alguma justificativa para só usar o beta dependendo do tempo?
No caso do dengue, a gente coloca o time dependence no beta, porque a gente vê que existe uma diferença na época de transmissão, se você está na época que tem mosquito, na época que não tem mosquito. Portanto, isso é para representar a sazonalidade. Se eu tiver o vetor, por exemplo, ele não vai estar no meu beta, ele vai estar no burst rate do meu vetor.
Sim.
Portanto, esse parâmetro time dependent é baseado no que eu quero descrever com o meu modelo. Por exemplo, no modelo do COVID, eu tenho mais de um parâmetro que é dependente do tempo, porque existe, por exemplo, uma variação na quantidade de testes realizados durante o período da pandemia. Então, esse parâmetro de detecção, ele é time dependent também. Não só o de transmissão, mas o de detecção. Portanto, isso vai depender do que você quer responder, do que seu modelo vai mostrar.
Ok. Ok, então no modelo de Covid seu, vocês usam também mais outros parâmetros dependentes do tempo.
Tem parâmetros de dependência no testing capacity, tem parâmetros de dependência no hospital admission, porque com o tempo você tem mais camas, você adquire mais possibilidade de, né, de aceitar as pessoas no hospital. E tem o transmission rate, que é sazonal, porque é uma doença respiratória. Portanto,
sim. E seus dados, eles te dão essa informação? Os dados que você trabalha com eles te dão essa informação?
Sempre. E ter os dados que te dão essa informação é essencial.
Com
você
certeza.
Só justifica o que você tem, você só justifica o que você pôs no seu modelo com dados.
Sim, e você faz tratamento de dados? Você usa algum tipo de tratamento de dados?
Como
por
assim,
exemplo, a parte... você usa alguma coisa bayesiana, alguma estatística bayesiana, alguma coisa por trás?
A gente usa likelihood functions para poder descrever as inseguridades, né, as seguranças, eu nem sei se essa palavra existe. Mas os dados que a gente tem, a gente tem que ter uma definição muito boa dos dados, né? O que é um caso positivo, o que é um caso hospitalizado. E depois que a gente valida o modelo, calibra o modelo com esses dados para cada uma das variáveis que você tem, a gente faz o likelihood, a gente usa o likelihood function para poder ver a insecurity, né? A insegurança.
Ok.
Sim.
Ok. E esse banco de dados que você usa é alguma coisa do governo? É ligado ao governo?
No caso do Covid, é diretamente do governo que a gente recebe, e foi, né, depois a gente conversar mesmo com o pessoal da saúde pública, o que a gente precisava, e eles tratavam, os dados são excelentes, mas é uma coisa do governo. No caso do dengue, os dados são públicos, são do Bureau de Epidemiologia da Tailândia, no caso, ou eu tenho casos do Ministério da Saúde da Colômbia, ou alguma coisa assim. O importante é que você tenha os dados, que você saiba o que esses dados são. Não é para a gente pegar uma lista de número de casos, se você não souber número de casos, como, quando, né? Você tem que ter uma definição muito boa de cada um dos dados que você tem, mas são necessaríssimos, muito importantes.
Ok. Muito obrigada, Maíra. Parabéns aí pelo trabalho. Sucesso.
Gracias, Sandra. Bueno, ha sido todo un placer escucharte, Maira. Estamos seguros que volveremos a contar con tu presencia. Muchas gracias también a todo el grupo por haber permitido hacer la invitación a Maira. Maira, thank you very much, Maira.
Well, muchas gracias, Rosana. Gracias.
Ok, Sandra, paso contigo.
Ok, gracias, Rosana, Maíra y